All right, in this video, we're going to talk about qualitatively why a CV, a cyclic voltammogram, has a peak shape. Why does it have this peak shape instead of being just a constant line going up, or it reaches a plateau and then it's flattened off? Okay, so the short answer is that this is an interplay between driving force, okay, which we can think of as in terms of overpotential, the voltage applied, the voltage that's beyond the thermodynamic voltage, right, versus diffusion effects, okay? And so the way to think about this is that if I drew it this way, right, let's say this is, in this sort of plot, this is my voltage in volts, which is a proxy for the driving force that I'm applying to the reaction. And this is my current, or current density. Could be in amps or amps per centimeter squared, electrode area, something like that, or milliamps. So if we're getting positive current here, let's say this is a value of 0, this is a positive current, and we're talking about voltage, and we're going to more positive values. So this is more positive. We're favoring oxidation. That's what happens in a CV. So let's think about a prototypical reaction like ferrocene going to ferrocenium. That's an oxidation reaction. Fundamentally, what's happening there, right, is iron 2 sites are being oxidized to iron 3 sites. So we know this peak is due to that happening, but why is it a peak shape and not one of these other shapes when we do a typical standard cyclic voltammogram? Why most time do we get a peak, not one of these shapes? Well, let's imagine we have our electrode surface. And at the beginning of the experiment, low magnitude voltages down here, we have a bunch of iron 2, our reactant, on the electrode surface. Okay? Now, as we increase the voltage, nothing happens until we reach a point somewhere where we're past the standard reduction potential, the thermodynamic potential, where this reaction can occur. So we'll call that E naught. Now, it might take a while to go past the E naught before this happens, depending upon the kinetics of the reaction, right? But at some point, we're going to be applying a strong enough oxidative driving force to start this reaction. And that's why we get an increase, and in this case, if I'm using the IUPAC nomenclature, of positive current. So we get an increase in positive current. And what's happening there is there's enough driving force that very slowly, some of these iron 2s are getting converted to iron 3s. And then, slowly another iron 2 from solution can come to the electrode and wait until it becomes an iron 3. As we go to more and more driving force, more and more overpotential, more and more positive voltage, we are doing this process faster, okay? At least the conversion step we are doing faster, the electrochemical step. The step of iron 3 going away and iron 2 going in, that is a diffusion control process, right? That's just diffusion of ions out because there's a concentration gradient, or diffusion of ions in. So that part stays the same. The diffusion rate stays the same, but this conversion rate speeds up. And we keep speeding up with more and more driving force until we get to the peak. And at the peak, the way to visualize this in a qualitative way is that all of the reactant, all of the iron 2s on the surface of the electrode get converted as fast as they can to iron 3s. And so now they're all iron 3s. So then why does the current go down? Because that's the key, right? The current goes down. If the current goes up, we understand now why the current's going up. More driving force. More driving force. Why is the current going down? Because now you must wait for more iron 2s that are in the bulk solution to diffuse back to the electrode to react. And the iron 3s also have to diffuse away from the electrode. So you have depletion. You have diffusion-controlled depletion at the electrode. Okay? And if you look carefully at this, you reach a point where there's a flat line. This is supposed to be a flat line in my drawing. Okay? This is what we would call steady state current. This is a steady state regime. So you sort of have these three regimes, four regimes. This is, nothing happens below, not enough driving force, not enough driving force. You have more driving force, enough driving force to get the reaction going. It's going faster and faster, faster. Then you have this diffusion control peaking, so the current goes down, and then you have a steady state. And at the steady state, you've established an equilibrium between diffusion of reactants out, or diffusion of reactants into the electrode and of products away from the electrode. So that's why you get this type of shape in a CV. Of course, the exact same thing happens when you have a reductive type of current, where you have these regimes, but now things are flipped, right? We're going more negative voltage. So if we're thinking about now iron 3 going to iron 2, negative voltages going to the left. We have not enough driving force. Maybe E naught is somewhere here. It could be here. Right? It depends on the kinetics of the process. But once we get enough overpotential, now more negative than our E naught, right? We're going to be able to start that reaction. We go more and more negative, more and more driving force. Then we reach a part where we have depletion controlled by diffusion. And then we reach a steady state current due to the equilibrium of products coming out and reactants coming in. And then, of course, if we put these together, we have the typical duck-shaped CV that we all know and love, right? And so that's how it looks together. Now, so you don't get this because this would mean that the reactants, the system's never diffusion controlled. You could get that if you haven't gone far negative enough, right? If you're just zoomed into this part of the CV, if you haven't gone to enough driving force, let's say, more positive, positive enough in this case, you might get something like this. Okay, this is a case. This type of shape is a case that you get when you do rotating disk electrochemistry. I'll talk about that in another video.